Hi, this is our refrigeration presentation. Presenting with Harrison, Dilling, and myself, Josh. Today we'll be talking about the introduction, system description, calibration, the initial results, as well as some of the next steps we'll be taking. The main goal of this lecture is to model the system, specifically the inputs and outputs of the compressor and vortex tube. Additionally, we will be looking at the capabilities of the system via the energy transferred. Starting in week 1, we will be analyzing the steady state analysis using the compressor. In week 2, we will be analyzing the transient response for the compressor and building air. Some of the outputs that will be analyzed include the thermal resistance and the load material properties. In the reverse Brayton cycle, there are 4 main steps. Air is taken in at room temperature and pressure. The air is first pressurized in the compressor. Next, it is cooled in the heat exchanger but maintains its pressure. It is then passed through a vortex tube which rejects the hot air and allows the cold air to continue. Lastly, the cold air passes through the load while allowing it to be chilled. Since this is an open loop system, it returns to the surroundings.
Taking a trial run at 0 volts was necessary for later data collection and analysis. This run was used to calibrate the measurement sensors, as the pressures, temperatures, and flow rates when the motor is at 0 volts are all known. Temperatures and pressures were offset to their ambient values of 294.05 Kelvin and 104 kilopascals respectively, and flow rates were offset to 0, as there was no airflow when the motor is at 0 volts. After all the data for each voltage trial is collected and offset, these temperatures and flow rates were plotted versus input pressure, P3. This allowed us to check the validity of the relationships and their regression approximations. Plot 1 being negative exponential relationship, plot 2 and 3 being positive linear relationships, and plot 4 being a positively logarithmic relationship. Next, we compared experimental calculations for R insulation, K insulation, and Q dot ambient, the heat transfer rate to the surrounding air. These results showed that K insulation values are higher than theoretical value of 0.03, and also thus our R insulation values are much lower than theoretical. And this is due to the assumption that the load block was insulated on all 6 sides, when in reality only 5 sides are insulated. This causes more heat to be able to escape from the load block and results in the data reflecting that the styrofoam insulation block is a quote-unquote worse insulator than it theoretically should be. This is resulting in the discrepancies seen between theoretical and experimental Q dot ambient calculations.
So these are our values for steady state uncertainties. The uncertainty of Q dot ambient does not vary with voltage at steady state, whereas the uncertainty for Q dot air and R insulation do vary with voltage even during steady state. It's kind of hard to put these numbers into context without knowing what our Q discrepancy for week 2 is going to be, but just at first glance they seem reasonably low and around what we expected. So looking forward to week 2, we'll be doing a transient analysis of the refrigeration system. Once again, before doing this analysis, we'll have to collect offset values for our sensors. And then once calibrated, we'll be doing 2 different trials of the system. One will be using the compressor at as close to 40 psi as we can possibly get using the voltage to pressure calibration equation. After this, we'll be using the building compressed air, which is going to be at 80 psi. In doing so, we'll be able to effectively compare how air pressure affects the transient response of the system. In particular, we want to examine how this pressure affects both the rise time and the steady state temperature of the response. So once we've performed these trials, we're going to do a load energy balance using both the sets of data, one using the motor and then one using the building air, as well as the R insulation value calculated from week 1. So solving for Q load, Q ambient, and Q air is going to allow us to find the value for Q discrepancy, which we think is going to serve as a good benchmark for how good our system model is. And then looking forward towards week 2 expectations, So kind of our main expectation is that we expect the system to reach a much lower temperature. I guess the temperature of the load to be much lower when using the higher building air pressure as compared to the motor compressor. We're also expecting to be able to validate the effectiveness of the system parameters and assumptions and resembling theoretical expectations of the system. And then we also want to compare to uncertainty. So like I mentioned, we're going to solve for Q discrepancy, compare that to our uncertainty, and be able to decide how good of a model our system is. And then once we have that, hopefully we're going to come up with some possible system improvements we can make to decrease this Q discrepancy. All right, and that's all we have. Thanks, guys, for your time.